Welcome again to another video. In this video, we'll be solving question number 310 and that is marked medium. So let's first understand what we have to do in the question. So we'll be given a tree of n nodes labeled from 0 to n minus 1 and an array of n minus 1 edges where edges of I equal to a comma b. Also the graph will be an undirected graph, right? So that means the edge between AI and BI, it's an undirected graph. So we can go from A1 to AI to BI, and also we can go from BI to AI. We can choose any node of the tree as the root. So let's make a tree. Imagine 1 is here, 0 is here, 2 is here, and 3 is here. We will be using this same tree for the dry run as well and understanding the question. So this is a tree because there is no cycle here, and also the edges are undirected. So the question states that we can use any node as a root. So that means this can be the root, this can be the root, this can be the root, and this can be the root. Now what does being a root mean? Being a root means that we will start the traversing of the tree from that particular node, right? So if we choose this 2 as the root node, that means we'll be starting our traversal from 2. We'll go from 2 to 1 to 0 or to 3, right? Now where do we want to go? We want to go to the last possible leaf, right? So that means if we start from 2, we move to 1 and we move to 0. So from 2 to 0 there are 2 edges. So the height of 210 is 2, right? Let's write that down. Height of 2 comma 1 comma 0 is 2. Similarly, height of 2 comma 1 comma 3 is also 2. So the minimum possible height is 2 when we choose 2 as the root node. But if we choose 1 as the root node, we can only go one way, right? We cannot go back. So in the case of 1, when we choose 1 as the root node, we start traversing from 1. So the height of 1 comma 2 is 1, height of 1 comma 3 is also 1, and height of 1 comma 0 is also 1. So the minimum height for root 1 is 1, and that will be our answer. For this tree, the answer is 1. 1 as in not the height, but the root node of 1. That means we are saying that if we select 1 as the root, then we get the minimum height possible, right? So that means we are returning an array of nodes, which if we choose as the root, we will get all the minimum possible height. Okay, so if there are other nodes other than 1 whose minimum height was 1, we would have included that node as well. So that is the question. So imagine this is the tree, right? This is the tree. Okay, now say we chose 1 as the root node, right? We have chosen 1 as the root node. That means to find the minimum height for 1, we need to traverse from 1 to 2, 1 to 3, 1 to 0, right? For this traversal, we find 1, for this 1, and for this also 1, and the minimum of all those is 1, right? So what I'm trying to say is, if we traverse from the root to the leaves, for every single root we have to traverse multiple times, right? If we chose 1 as the root, we'll have to see every possible path that is going away from 1 to find the minimum, right? But if we do the opposite, What do I mean by opposite? If I start traversing from 2, if I start traversing from 2, in order to find 1, how many traversals do I have to make? From 2 to 1. If I start traversing from 0, how many traversals do I have to make? From 0 to 1. Then from 3 to 1, right? We are still making 3 traversals, but we are not stuck at 1, right? If we would have started traversing from the root, the loop would have been something like for root, for every root for each neighbor, right? That means we would have done an n square time of loop, right? But in this case, when we are traversing from leaf to root node, what we can do is for every leaf, just go wherever it wants, see if it leads to, if we find root, modify the answer equal to minimum of whatever we have found or whatever it was stored, right? So in this case, we only have to do a single, basically n complexity of traversal, right? So that's why we will start traversing from the leaf towards the root. So one thing that we have understood is, instead of traversing from each root to each leaf node, we should traverse from leaf to root, and along the way we should keep updating the answer, right? Now let's see another concept, which is this 2, 3 and 0 are at equal distances from 1, right? Are at equal distances from 1. So if I start traversing from each of these nodes simultaneously, I'll reach the one node at the same time, right? Meaning the minimum distance of each of the cases would be same. Minimum would be same, right? So that means, say there are this kind of nodes 1, 2, then 3, 4, 5 and 6, right? What will the answer in this case? If we take, say, 5 as the root node, we'll have to traverse from 5 to 1 and 4. So the answer would be 3, 1, 2, 3. If you take 6, same answer, 1, 2, 3, or 1, 2, 3. We cannot take, of course, we cannot take this because we have to take the longest possible, and that should be the minimum. So, okay. So, and for 3 and 4 also, the answer would be 3. But for the roots 1 and 2, the answer would be what? 2 in this direction, 1 in this direction. So that means the answer would be 2, right? We have to choose the longest one. For 2 also, it's a 2 edge, 2 number of edges. So both have 2 as the minimum height, right? So that means our answer would be an array of 1, 2, right? But if you notice a pattern at this moment, this is a leaf node, this is a leaf, this is a leaf, this is a leaf, right? If we traverse from all of these leaf nodes together, because we know leaf cannot be an answer, a leaf node cannot be an answer if it has nodes inside the graph other than the leaves. Leaf cannot be an answer, right? We saw this pattern. So if we traverse from all these leaf nodes together at once, right, we traverse through this, we traverse through this, we traverse through this, or we traverse through this, we are left with 1 and 2, right? We are left with 1 and 2, and that is our answer. That is the pattern that we'll use to find our answer, right? If we eliminate the leaf nodes, the remaining node will be the answer. Another important concept that we need to know here is an answer array will either be of length 1 or 2. We cannot have a 3 length array. Why? Let's imagine a node system or a tree with 3 nodes, right? So 1, 2 and 3. Imagine there were other leaf nodes, but those got eliminated, right? So we are left with 1, 2 and 3. But even after, when we are left with 1, 2 and 3, we can still eliminate 1 and 3, and the answer would be 2, right? So in that way, in our answer, we'll always have either 1 node or 2 nodes at the maximum. So let's try writing the code for this, and it will make more sense. Okay, before that, let's see another concept, which is, I give this example 1, 2, 3, 4, 5 and 6, right? So as I said, we'll start traversing from each of these nodes simultaneously, or we can, another word for this is, we can say we are eliminating these 4 nodes and the remaining would be 1 and 2, and that would be our answer, right? But how will we know that these 4 nodes have to be eliminated simultaneously and not include the 2 in that group, right? We could include 2 along with 3, 4, 5 and 6, but why are we not? So in that case, we'll maintain an array. We'll be maintaining an array. So let's say, so 1, 2, 1, 2, 3, 4, 5 and 6, right? 1 will be 3. The value of first position in the array will be 3. Value of 2 would also be 3. But value of 3 would be 1. Value of 4 would be 1. 5 would be 1 and 6 will be 1. Why is that? Can you guess it? Because for 1, it is connected to 3 other nodes. 1, 2 and 3. 2 is also connected with 3 other nodes, but 4 is only connected with 1. 3 is only connected with 1. 5 is only connected with 1. And 6 is connected with 1. That means those nodes which are connected with only one other node will be a leaf node, and we have to eliminate them first. Imagine there was another node here, 7. In that case, 4 would not have been a leaf node, right? Because it's inside the graph. The leaf node in this case would have been 7 because only one connection. 4 would have had 2 connections then, right? So that's how we'll be finding the answer. So for this to work, we'll have to first make a graph, right? And we'll call the array that will keep track of the connections called indegree, right? Make array of int and. Now how will we make this graph? Basically, the graph would be something like, it will be an array of numbers. So basically 1 would be 2, 3 and 5. 2, 3, 5. 2 would be 1, 4 and 6. 1, 4 and 6. 3 would be 1, and so on, right? Basically we are keeping track of 1 is connected to which other nodes, 2 is connected to which other nodes, and similarly 3 connected to which other nodes. This is the graph, and again this whole thing will also be an array, right? So it's a 2D array. Okay, so let's make this 2D array. How will we do that? We'll say for underscore comma e range edges. So edges we are given saying that there is a connection between ai and bi, right? So let's say x comma y, e of 0, e of 1. This means X and Y are connected. X and Y are the two nodes that are connected via this edge, right? So what we'll say graph of X append graph of X comma Y. Basically include the Y node in the X's graph, right? Because they're connected. And similarly, graph of Y equal to append graph of Y comma X, right? As we saw, one's array has two. Similarly, two's array also has one because they are connected with each other, right? One's array has three, three's array has one. Next, as I said, we have to maintain a degree of connections, right? A degree of or an array of connections, basically saying in degree of X plus plus, because we just appended a new connection to X, so the number of connections of X should increase. Similarly, in degree of Y plus plus. Next, how will we traverse the graph? We have made the graph now and we need to traverse it. And as I said, we'll traverse it from outside, right? From leaf to the root. And the traversal technique that we can use is BFS, breadth first search, right? So for that we need a queue. So queue equal to array of int, right? And we'll also store a variable remaining equal to n, right? So remaining basically will say how many nodes are left to be processed, right? For now we have not started the processing of the nodes, so n nodes are remaining to be processed, basically the total number of nodes. Then for I equal to 0, I less than n, I plus plus, we'll say if in degree of I equal to 1, q equal to append q comma I. So this basically say, as we saw, which are the leaf nodes? The leaf nodes are the ones that have a in degree of 1, basically one connection only. Those are the leaf nodes, right? And we'll start traversing from the leaf nodes. So that's why in the starting we are just appending the leaf nodes to the queue, right? So then for remaining greater than 2, so this loop will run until we are left with only 2 or 1 nodes, right? That's what we want. As we discussed, the answer can have either 1 node or 2 nodes, right? So this loop will run until it has either 2 or 1 node, right? Then size equal to length of queue remaining minus equal to size. This means that currently in the queue we have this many size amount of nodes, and we'll process them parallelly, simultaneously, right? Not one by one. As we discussed, we'll start traversing from all the leaf nodes simultaneously. So that's why we are saying that reduce the remaining by this size, because these many nodes will be processed together, right? And for that, for I equal to 0, I less than size I plus plus, right? So current node will be q of 0, and for each node, as we saw, we will be traversing to wherever we can, right? So that means for underscore comma neighbor of the current node, so range graph of current. So as we saw, basically if we landed in this node, say we found 1 as the current node, we'll see from 1 where we can go from 1 to 2, we can go from 1 to 3, 1 to 5. So we'll iterate over this array, right? So that's what we are doing. We are iterating over that array. Then we'll reduce the in degree of neighbor minus minus, right? What does this mean? This means that we are processing the current node, so all the connections from the current node that we have to the neighboring nodes should be severed, should be cut, right? So if the connection is cut, the connection count array, basically in degree, should also be reduced for that particular node, right? So this means that particular node is still in the system or in the process. We have not processed that neighbor node, but the connection from the current node to the neighbor node does not no longer exist. So that number should be reduced. And then if after reducing in degree it becomes 1, that means it has turned into a leaf node and we can append it to the queue, right? So queue equal to append comma neighbor. We'll see why we are doing this, but that is done. And in the last we will be returning queue, right? Now why we are returning queue and what does this do, right? So as I told you, initially the 4 was a leaf node, but after adding 7 the 4 was no longer a leaf node, right? So let's do the dry run for this case. 1, 2, there was 4, then 7, then 6, then 3, and then say 5, right? Now these are the leaf nodes and they will get eliminated because they can't be the answer, right? So after eliminating those, we are left with 1, 2, and 4, right? So that means these nodes that were previously not a leaf node, just now after processing this batch of leaf nodes became the new leaf nodes, right? So the next time we'll have to process these ones and we're finally left with 2, right? So that means the queue array initially had these numbers 5, 3, 6, and 7. We processed those and added 4 and 1 to the queue. And after processing 1 and 4 as well, we added 2 to the queue because there was no connection left, right? So now we know the remaining is larger than 2. Sorry, the remaining is smaller than 2 or equal to 2. So that will be our answer stored in the queue because that is the array that was storing the nodes, right? We were adding nodes to the queue, right? So that's why in the last we also return the queue. Let's see if this works or not. Okay, wrong answer. Why is that? And that's because after processing the nodes, so this is where we process the current node or the batch of current leaf nodes, right? We have to remove them from the queue as well, which we forgot to do. So queue now becomes equal to queue size this, right? So that means remove the earlier nodes and save the newly added nodes for processing. So let's try seeing this. Okay, 3 comma 4. That's because, sorry, it should be I, not 0. Okay, so solution is working. Let's try submitting it. And we got a wrong. Very nice. This is an edge case which could be resolved by if n equal to 1, return array of int with 0 because that is the only available node in the tree, right? Okay, so that is working. Nice. So yeah, So that was the solution for this question. This method is actually called topological sort. Basically, we maintain an array of connections from between nodes, right? Each node has how many connections. If it is a directed graph, we store directed connections count, and if it is undirected, we store both the count. So basically, if imagine if this was a directed graph, we would have done only this and this, right? So it means it would have said we can only move from x to y, and so only increase the count of x, not y. So that was the method. It is generally used with breadth first search technique. It can be done with BFS, but I prefer this method, so I've done this. So yeah, that was the solution, and I'll see you in the next one.